यस। कौन सा टॉपिक आपका बचा हुआ है?
हेलो।
यस।
यस सर।
जैसे आपका टॉपिक ओएमसी बचा हुआ है, बाकी टॉपिक हो गए आपके केमिकल काइनेटिक्स, गैसियस स्टेट, थर्मोडायनेमिक्स और फिजिकल स्पेक्ट्रा।
तो फिजिकल स्पेक्ट्रम में मॉलिक्यूलर स्पेक्ट्रोस्कोपी का वो लास्ट पार्ट बचा हुआ है। इलेक्ट्रॉनिक स्पेक्ट्रोस्कोपी थोड़ा बचा हुआ है। लास्ट डे का थोड़ा बचा था इलेक्ट्रॉनिक स्पेक्ट्रोस्कोपी।
इलेक्ट्रॉनिक है, उसमें कोई ज्यादा नहीं है। इलेक्ट्रॉनिक के बेसिक प्रिंसिपल और डेरिवेशंस और लिमिटेशंस, ये चीजें कर लेना, ठीक है? क्योंकि अब टाइम नहीं है ना।
हम्म। जी सर।
ये चीजें, वो चीजें आप कर लेना, कोई बेसिक ही है। लिमिटेशंस, एप्लीकेशन, बेसिक और डेरिवेशंस, है ना?
यस।
आपका इंटरव्यू कब है?
तो 4 तारीख को है
तो कब जाओगे?
हमारा ट्रेन यहाँ से। सर 1 मार्च को ट्रेन है मेरा, मतलब
तो 29 तक आप दे सकते हैं, ठीक है?
1 मार्च।
26, 7, 8, 9,
जी सर।
4 दिन है, ठीक है? इसमें कुछ फाइनल हो जाएंगे,
तो
ठीक
कल
है?
मेरे को सर कल मेरे को कॉलेज जाना है, वो झाड़ग्राम जाना है, वहाँ से मेरे को बीएससी का सर्टिफिकेट लेना है, क्योंकि आज बंद था कॉलेज। तो वो कल का दिन नहीं हो पाएगा, बाकी 2 दिन बचेंगे, और वो बुधवार और बृहस्पतिवार।
ये तो जैसा भी है आप देख लेना, ठीक है? या आज हम स्टार्ट करते हैं ओएमसी। यस, व्हाट इज ऑर्गेनोमेटेलिक केमिस्ट्री, व्हाट द मेन बेसिक प्रिंसिपल ऑफ ऑर्गेनोमेटेलिक केमिस्ट्री?
यस। बेसिक तो ऑर्गेनोमेटेलिक और मेटेलिक केमिस्ट्री। The term organometallics come from this two term organo and metallics. So organo, this related to the organic molecules or organic groups or ligands. And metallics, in this chapter organometallic compound, we mainly study transition metals. So this metallics is from our transition metal. So in organometallic chemistry, we study transition metal complexes having organic ligands, having organic ligands, that is having metal carbon bond. So we study metal carbon bonds in organometallic chemistry.
यस, व्हाट द यूजेस ऑफ ऑर्गेनोमेटेलिक केमिस्ट्री?
Uses, yes sir. Just one minute. Uses, so the
Which factor affecting of OMC? How many factors affecting from OMC?
the uses of OMC, the organometallic compounds are used in many many reactions as catalyst. Now the ferrocene is used as an anti-knocking reagent in diesel. Diesel. uh, Aside from this, the TE tetraethylate TEL also used as anti-knocking reagent and smoothing our diesel the fuel. So the use of organometallic reagent is mainly as catalyst, that is hydrogenation. In hydrogenation, we use RHPPH3 whole thrice Cl, that is the Wilkinson catalyst, and we use the RNGX. This is an organometallic compound which is used in the forming carbon-carbon bond, and in the formation of the carbon-carbon coupling reactions, the organometallic reagents are used. Also for olefin metathesis, the organometallic compounds are used to form new double C carbon-carbon double bonds in olefin metathesis. So these are the uses of organometallic chemistry or organometallic reagent.
Yes. What is 18 electron rules and what's the difference between 18 and ENA rule? What the basic principle of 18 electron rules and ENA?
So the EAN is the effective atomic number, and this comes from our rule, that is the octet rule, that the atom must possess 8 electrons in their valence shell, and whereas the 18 electron rule says the charge on the valence electron of metal plus the electrons that are donated by ligand by convention covalently is equal to 18. So the molecules which possess 18 electrons are the stable molecules. So this is the effective atomic number EAN and 18 electron.
Any limitation and drawback of ENA and 18 electron rule?
Yes, sir.
Yes.
So the 18 electron, many compounds, that is the early transition metal compounds, that is cadmium, titanium, vanadium, this metal compounds, and also the square planar complexes, that is platinum, palladium, these complexes do not follow this 18 electron rule. They follow the 16 electron rule, and they possess 16 electron in their valence shell in total. If for EAN, that is we get from the Bohr model. So many this method of calculating the valence electron is very complicated or very complicated. So this is avoided, and 18 electron rule is used.
Yes. Next, what is metal carbonyl? What the main application of metal carbonyl in OMC? Explain briefly.
So carbonyl, that is CO, is the main ligand here in organometallic compound, that is metal carbonyl. Metal carbonyls are generally symbolized as MCOX, where X is number of CO ligands. This is an example of homogeneous metal carbonate. Metal carbonate. And if there is any other ligand, that is MCOXLY present, then it is called heterogeneous metal carbonate. So the metal carbonate bonding in metal carbonate is mainly two-way, as CO is a pi acceptor ligand. That is carbonate is a pi acceptor ligand. Acceptor ligand. So the bonding of metal and CO is, this is the vacant p or d orbital of metal, and this is the non-bonding electron of carbonyl that is given to the oxygen by sigma. This is the bonding, sigma bonding. And now the metal has high electron density, so it will give back its electron to the carbonyl in its antibonding. So the antibonding orbitals are like this. Plus minus, this is the antibonding orbital of CO, plus minus. So this is the field orbital. So this is the pi back donation. So this is the bonding of metal carbonate.
Yes. What is
This bond,
metal nitrosyl? What is the example of metal nitrosyl?
metal nitrosyls are, in metal nitrosyls the ligand is NO. NO is present, so NO is N as plus can be N O minus. So nitrosyl can be plus, and NO plus is when connected to metal. When connected to a metal, NO plus is linear in shape and contribute 3 electron donor as a 3 electron donor, where NO minus is bent in structure and 1 electron donor. So in metal nitrosyls, the metal nitrosyl in this case is like this, Ln. This is the metal nitrosyl when nitrosyl is in NO plus and N is NO minus. Nitrosyl in NO minus. This is the bent. This is the bent structure, metal nitrosyl. So this is metal nitrosyl. Nitrosyl. Yep.
Yes. What the purpose of any uses of metal carbonyl and nitrosyl in OMC? Explain.
Metal carbonyl. So metal carbonyls are used in various reactions. So metal carbonyl in formation of shock carbon, sorry, Fischer carbon, formation of Fischer carbon complex, and metal carbonyls are used in use
Yes.
uses
Good.
अभी
Yes, yes.
सर मेटल नाइट्रोसेल का यूजेस अभी मतलब पढ़ा नहीं है सर, वो पढ़ना पड़ेगा।
Yes.
नाइट्रोसेल
Yes. Next, move on. Phosphines. What is phosphines? What is the main application of phosphines? Explain. Now, how many types of phosphine?
Yes, sir. So phosphine is phosphorus compounds. Phosphine. So phosphine, these are generally written as PR3, just like NH3. The PR3 is bent structure. It has a non-bonding electron like nitrogen, so it can act as a donor as well as acceptor. So the donation of a non-bonding electron to metal occurs by sigma bonding P R3. This is the bonding interaction, sigma donation. And the pi back donation,
Yes. Monodietri. Phosphines example.
examples. Yes, sir. Phosphines are the examples of metal phosphines are in RHPPH3 whole thrice here. So here PPH3 is an example of phosphine. Another example is PCY3, where CY is a cyclohexyl group. Another example is PME3, POME whole thrice, PX3. These are the examples of metal phosphine. This phosphine affects the the metal carbon bonding, and as well as the stretching frequency of the metal carbon. So they affect the metal C triple bond. So if the donation to the metal is increased, so delta minus increased here. So back donation to the CO increases. So here metal, carbon, bond strength increases, implying the new, that is the stretching frequency of metal carbon increases, and the stretching frequency of carbon oxygen decreases.
Yes. Next is what metal carbines and metal carbonyls. What difference?
Metal carbon. So we have to first understand carbon and carbide. So carbon is generally two electron deficient molecule, Cr2, and this is a tri-Cr. So if I draw the structure, so this is the this is the singlet carbon, and C R R. This is the triplet carbon. This is called singlet carbon because they have the spin of the electron, total spin is 0. So spin multiplicity 2s plus 1 is equal to 1. This 1 represents the singlet, and in this case the spin is equal to half plus half is equal to 1. So 2s plus 1 is equal to 3. So 3 represents the triplet state. So these are the two type of carbon. Similarly, the carbines are CR and this side. So 1, 2, 3. This is the two spin is, and this is carbines. So when this type of ligands attached to a metal are called metal carbines and metal carbines. Now there are two type of metal carbines. Now if I specifically tell the metal carbines, so metal carbines, there are two types of metal carbines. Two types of metal carbon. One Fisher carbine. It is named after the scientist who or chemist who who discovered this type of carbons. And this is called Fisher carbine complex. To study Fisher carbine complex, we have to generally understood the idea the carbon that is attached is X, Y. Here metal is in low oxidation state, generally within +2. So low oxidation state means less than equal to +2, and the X and Y here are the electronegative atoms or groups like OM, NR2, NHR, OH, etc. These are the X and Y, and this type of carbons are electrophilic in nature. Electrophilic in nature. This Fischer carbon is in the carbon is in singlet state. Okay. To represent the bonding, we have to draw the skeleton with orbitals. So the orbitals, if I draw Ln metal, if I just forget about the substituent ligand L, M, is the metal PLT orbital, carbon is OM, and this is ISR. So the d orbital of field d orbitals of metal, and this is the empty p orbital of the carbon. This is empty, and plus minus, this is plus, then this plus minus minus, this is failed. So this is pi back donation. So here this is sigma donation and pi back donation, both occur. So this double bond generally represents this type, two types of donation in Fischer carbon. Now if I talk about shock carbon, so in shock carbon, complex, so this feature will be shock shock carbon. So in shock carbon, metal is in high oxidation state, greater than equal to +3. The substituent ligand, these ligands are non-pi acceptor ligand, and in case of Fischer carbon, the ligands will be pi acceptor ligand. They are non-pi acceptor, like, and this X and Y are the organic groups. X, Y, maybe pH, maybe Me, hydrogen, etc. The carbon is nucleophilic in nature, nucleophilic, and this is a dianionic ligand. This carbon is dianionic ligand here, and the type of carbon in used in shock carbon is triplet carbon. And the example is Me5Ta. The example is Me5Ta double bond C, CH3 H or C, Ma3. This is the shock carbon, and the bonding in shock carbon will be so bonding metal metal empty orbital, and metal has one electron here. The carbon is in triplet state, so it has also one electron. This is a covalent bonding, shared electron, and this is the p orbital. This is not vacant now. It has also one electron. This will be opposite spin. PH3H. So is that now d orbital. So it has also one electron. So this is the also one bonding interaction. Minus plus. So this is the bonding interaction in shock current complex. This is the bonding interaction between the carbon and the metal in shock carbon complex.
Yes. Yes. What is the limitation of Fisher and Short carbon?
So limitations. So Fisher and shock carbon are the two boundaries. Fisher and shock. In one side is totally singlet state, and here totally triplet state. But most of the molecules reside in between them. So there are Grubbs catalyst, Grubbs first gen and second gen catalyst, they, which shows some properties of Fisher carbon and some properties of shock carbon. So these are the two ideal systems on the two opposite sides, but none of them totally explains the Grubbs catalyst. The Grubbs catalyst has the property of both Fisher carbon and the shock carbon. So this is the major limitation of Fisher and shock carbon.
Yes. Good. What is hapticity, denticity? What the main application of hapticity, denticity? Explain one by one.
Yes, yes, sir. So there are many molecules, there are many groups that can donate from more than one point. So as taking an example of cyclopentadienyl anion. So this is a cyclopentadienyl cation anion, cyclopentadienyl anion. This anion, when binds to a metal, so it can bind to a metal with bind to a metal with one center, like this is called eta 1, as one represent metal binds to the carbon center, the center of a group in one, and it can connect as eta 3, that is, let's draw this. So this is eta 3. So this eta 3 complex. So in this case, the metal is connected with the 3 donating atoms of cyclopentadiene, or it can connect with the all 5s, where can be drawn like this, and it is called eta 5. So this is this eta 1, eta 3, and eta 5. These are called the hapticity of a ligand. So number of donor side of a ligand is called hapticity of a ligand.
Yes, good. What is flexionality and of compound? Any explain eta 1, eta 2, eta 3, 5.
So flexionality comes with the term with multidentate ligands. So as I was saying, the flexionality. So many groups or ligands so fluxional behavior. So what is fluxional behavior? So compound like Fe, CO, eta 5 and CO. This is 2 plus 2 plus 2 6 plus Fe 8 plus 5. So this is Me. So (18 electron system). Now if it reacts with another ligand, the substitution occurs. So PPH3. So it changes its hapticity during the reaction. Eta 3, Fe, CO, Me, PPH3. Now after that it is in eta 3 state. Now one of that CO leaves. This is the association, and one of the CO leaves and eta 3 turns to again eta 1. So Fe, PPH3, Me, CO. This is again 2 plus 2 plus 1, 5, 5, 5, 10, 18 left. So it is again eta 5. So the change in the hapticity from eta 5 to eta 3 to the molecule, the ligands can change their hapticity during the course of the reaction. This change in hapticity is called fluxionality or fluxional behavior.
That's good. Yes.
Of a
That's good. Yeah, next day we will discuss the left part of AMC. Yes, no?
Yes, sir.
Yes, good. Yes, metal crystal. Yes, homogeneous, heterogeneous catalysis, polymer, metallolysis, Waker process, hydroformylation of alkenes, cross reaction, coupling reactions, polymerization. Yes,
After that.
Yes, after that a final 1 to mock. Yes.
Final on
Yes, final is today you left no 28-29 final mock. Yes.
28-29 one day